Okay, so let's move to the second section now. This is just to remind you about the corpus that we are dealing with. This is the Reuters corpus. It has about 800,000 news articles. Each article has about 200 words on an average. And in the corpus as a whole, there are about 400,000 distinct terms. The average number of bytes per token is about 6, but this includes spaces and punctuation marks. And without spaces and punctuation marks, the average number of bytes per token is 4.5, but the average number of bytes per term is 7.5. And this is larger because most of the words in any document tend to be short words. And those short words are the more frequent words. So the most frequently occurring words in the English language are short in length, which is why averaging over tokens gives rise to a smaller value. But averaging over terms yields a larger value because each word is weighted just once when you are taking the average over terms, because whether it's a stop word or whether it's a very rare word, both are weighed equally here. But they are weighed unequally here, which is why the value is smaller, because stop words and other frequently occurring words are shorter in length. And finally, we are going to assume that our index is not a positional index. So we are looking at the simpler case of a non-positional index, and there are about 100 million postings in that index. And note that 100 million is less than 800,000 times 200. So we're going to spend some time looking at this table. And again, the data in this table is based on this Reuters corpus. And what's important is not the values per se, but some of the patterns that you would see in the data. So this part of the table, these three columns correspond to the dictionary of the index. These three columns correspond to the postings of the index, assuming a non-positional index. And if we go for a positional index, then these three columns give you some data about that. So let's look at the base scenario, where what we do is we parse these 800,000 documents in the Reuters corpus, and we split each document into its tokens, and we don't do any kind of sophisticated linguistic pre-processing here. Okay, so assume no normalization, no linguistic pre-processing. In that case, the size of your dictionary turns out to be about 484,000. So this size is in thousands of words or terms. So there are 484,000 terms in your dictionary if you don't do any normalization. The number of non-positional postings in such a scenario is about 109,000 or 110,000. And the number of positional postings, if you were to go for a positional index, is about 200,000. So clearly this has to be less than this, because in here each posting is not just recording the occurrence of a term in a document, but it's recording the occurrence of a term in a document at a particular position. So if a term occurs 10 times in a document, it's going to be recorded in 10 different postings. Whereas here it's just going to be recorded once, and so this size is smaller than this size. Now let's do let's do some linguistic processing where, let's say, we just discard all the numbers. All the tokens that correspond to numbers are just thrown away from the index. In that case, your terms come down by about 10,000, which is not a very significant difference. About 2% of the tokens were numbers, and so you get a minus 2% change in the size of the dictionary. Whereas in case of a non-positional, if you look at the postings list of a non-positional index, the number of postings also come down by about 8%, and they come down by about 9% in a positional posting. So again, these are just values that are empirically observed. There's nothing significant about them. So what's interesting is, um, if you do case folding, that is, if lowercase and uppercase letters are mapped, or lowercase and uppercase versions of a word are mapped to the same equivalence class, they're mapped to the same term, then notice that the number of terms in the dictionary come down to about 400,000, 390,000. So that's about a 17% further decrease in the size of the dictionary. So with both of these, the change is about 19%. So this column is recording the cumulative change relative to this base case, whereas this column is recording the incremental changes as we are adding each of these pre-processing phases. Now what's interesting is that if you do case folding, there is absolutely no change in the number of positional postings. And that's, if you think about it, it's intuitive, because by changing the case of a word, you're not changing how many times that word is occurring in the documents. So you will still have a separate posting for every occurrence of that word, whether it's an uppercase or a lowercase. But in case of a non-positional index, okay, so when we do case folding, there is a slight decrease in the number of non-positional indexes, non-positional postings, and that's because occurrences of lowercase and uppercase are now going to be collapsed to the same term, and so by treating them as one and the same word, or one and the same term, they won't be treated differently, and so there'll be a slight decline in the number of non-positional postings. Right. Now, these two are probably the most interesting rows here. Let's say you remove 30 stop words, the top 30 stop words. Again, how do you detect a stop word? You sort each of the terms in the dictionary in decreasing order of their collection frequencies, and then you choose the top 30 of those terms. So those will be the top 30 stop words. If you remove the top 30 stop words, there isn't much change in the number of terms, because the number of terms has just gone down by 30, right? So if it was 392,000 earlier, you're just going to delete 30 more terms from the dictionary, and so that's a negligible change. It's -0. It's a very small and negligible change. But if you look at the number of postings in the non-positional index that go down, go down by about 14%. And if you remove the top 150 stop words, again, I mean, the change in the decline in the number of terms is very insignificant, but you can see that you are decreasing the number of postings by about 30%. And if you look at the positional postings, so this was, why is this number high? Because these 30 stop words or these 150 stop words occur in so many documents, right? And by deleting those stop words, you're deleting those long postings lists. But if you look at the positional postings, not only are they occurring in so many documents, within a document they're occurring so many times. And so by deleting these stop words, there is a significant decrease in the size of your positional index. If you add stemming, again you expect to decrease the size of your dictionary, because many of the stemmed words will map to the same term. So words that were earlier different are now going to map to the same equivalence class, and so there's a decline in the size of the dictionary. And there is a slight decrease in the number of non-positional postings, because all those different words were present in their own postings. Like they had their own postings list, but now they're going to have a single postings list. They'll all be collapsed into one single postings list. And if there were different forms of a word appearing in the same document, that's just going to contribute a single posting. because all those different forms map to the same term. But if you look at the change in the number of positional postings, that's exactly zero. There's absolutely no change because stemming does not reduce the number of tokens ultimately, and each token is going to map to a positional posting. So since the number of tokens remains unchanged by stemming, there's no change in the number of positional postings, right? So this is the intuition for the various zero entries. Okay, and you can go through this table later on and try to argue for yourself why these changes are intuitive. Don't worry about the exact numbers, but this is a small decrease, this is a large decrease, this is a very 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 insignificant change, this is absolutely no change. You can intuitively try to examine and analyze why such patterns are seen when you do different kinds of pre-processing. So these correspond to different pre-processing steps. Now compression is of two kinds broadly. There's something called lossless compression and there's something called lossy compression. Lossless compression, as the name indicates, is compression where there is no loss of information. Okay, so all information is preserved. You can exactly reconstruct the original data from the compressed data if you employed a lossless compression technique. Lossy compression, on the other hand, is when you allow for some of the data to be lost. And the advantage of lossy compression is that it allows you to compress the file to a larger degree. You can make the file smaller if you employ lossy compression. But you can't reconstruct the original data because you will be discarding some of the information. Right? So some of the information that you evaluate to be non-important will be lost. So you won't be able to exactly reconstruct the original data. Now, the pre-processing steps that we just saw in the previous slide, which ended up reducing the size of the index, right? We decreased the size of the dictionary by about 33% by adding all these. We decreased the size of the non-positional and positional indexes by about 42% and 52% relative to the original state. Right, so these are examples. These can be looked at. These pre-processing steps can be looked at as examples of lossy compression. And why is this compression lossy? Because when you delete stop words, when you do case folding, when you add stemming, when you delete numbers, you are no more able to reconstruct the original documents from the index itself. Okay, that's why uh, this is called lossy compression. Whereas if you look at the index in the base case, right, just from the index you can reconstruct all the documents that you had earlier because you're not throwing away any information. Each token is being added as it is to the dictionary, and each token is going to enter into the positional postings. So you'll be recording the positions of the terms also, and so using the information in the index you can exactly reconstruct the original documents. So pre-processing can be thought of as a form of lossy compression. What we're going to mostly do in this chapter is we're going to look at examples of lossless compression. We're going to try and reduce the size of the index such that there won't be any loss of information as a result of the compression. So obviously you can combine this kind of lossy compression with the algorithms that we'll be talking about here for lossless compression. Now lossy compression will also make sense in a later chapter where the idea is that because most of the users of a search engine or an IR system won't be looking at the results beyond the top 15 or top 20 results, it makes sense to kind of ignore those postings or drop those postings which you will never figure in the top 10 or 15 results. Right? So we can shorten postings lists by just deleting from them in certain ways. I mean, right now you may not be able to understand how because we haven't looked at how postings lists, documents are ranked. But if we are able to figure out in advance that certain postings will not, certain documents are not going to appear high, are not going to rank highly, then we can remove the postings for those documents, for those particular terms at least. For those particular queries, if we know that the postings lists are not going to have, that the posting lists are not going to have certain postings in the top 20 results, we can safely discard them. So that's going to be another kind of lossy compression that we'll be doing. So don't worry about this right now. We'll look at it in a later chapter. So uh, let's now move to trying to estimate the size of um, your dictionary and the postings list, right? So if you want to build a search engine, you'll start with some corpus, and you may, in order to design your system, you may want to know in advance, you may want to estimate in advance how many terms you will have in the dictionary, so that you know in advance whether or not the index that you build will finally be able to fit the dictionary in that system or not. You can choose your hardware accordingly. So it's useful to be able to estimate the size of the term vocabulary just from the corpus itself, without actually, before you actually build the index. So how do we estimate the size of the term vocabulary or the number of terms in the dictionary? Well, one very crude upper bound on the number of terms will be, if you decide that I will have at most terms of size 20 in my dictionary, then I can estimate how many different strings of length 20 are possible, and that will be an upper bound. But obviously this is not a good upper bound, because the vast majority of these strings are not going to be valid terms. The other thing to note here is that even if you have a very large corpus, and as you keep adding new documents to your corpus, like in the context of the web, at no stage is your vocabulary size going to flatten out or become stable. As you're adding more and more new documents, you will find that your vocabulary size will keep growing. Okay, your vocabulary size will never plateau out. It will never flatten out. It will keep on increasing as you add more documents. And this may sound strange initially, because after all, you can say that there are only about 600,000 or so words in the Oxford English Dictionary. So why should, at some stage I should be able to capture all the words in the dictionary, and so why would adding more documents add more terms to the dictionary? And that's because these extra terms that will continue to appear in the vocabulary will correspond to things like, names of new startups, names of new people, new email addresses. There are always new tokens that are appearing in documents that are new. And so your vocabulary will keep growing with the collection size. And especially with Unicode, documents appearing in so many other languages, you can expect more heterogeneity in online documents, and that's going to also increase the size of your vocabulary with so many documents in so many languages appearing online. Now there is an empirical law called Heaps Law, which is an empirical finding. So there is no mathematical proof for why this law holds. It is just something that this this guy by the name of Heaps noticed in the late 1970s, that if you have, let's say you have a corpus in which there are T tokens. Okay, so T is the number of tokens in your corpus. Then what he saw was that the number of terms in the dictionary, or the size of the vocabulary, can be expressed as a power law. Okay, so there is a formula. You can express the relationship between M and T by this power law formula. M is equal to some constant K times T to the power some other constant b. Okay, so typically values of k are about 30 to 100, and the typical value of b is somewhere around 0.5, not very far from 0.5. So that means m is approximately k times square root of t, approximately. Okay, so if you plot this, so if you plot the number of tokens in your corpus and the number of terms in the dictionary, you're going to get something like this, because this is how the graph of y equal to k times root x looks, right? And it never flattens out exactly. Even if you keep on adding more and more tokens, if you keep on increasing the size of your corpus, this will go on increasing. It will never become flat. The number of terms in your dictionary will never become flat. So if m is k times t to the power b, log of m will be log of k plus b times log of t, right? These are simple. This follows from the simple properties of logarithms. Logarithm of x to the power y is y log x, and log of a times b is log of a plus log of b. So if you plot log m versus log t, okay, if you make this as the independent variable and this is the dependent variable, now you have a linear relationship between log of m and log of t, because k is a constant and b is a constant. So log of k is also a constant and b is also a constant. So this is an equation of the form y is equal to uh, mx plus c. Okay, typical linear equation, and it's the simplest possible relationship you can think of between two variables. But this is in the log space. So you're plotting log of t versus log of m, and you find that this relationship is linear. And again, I repeat that this is an empirical finding. It's an empirical law. It's something that's actually observed for real collections. It's not something that is mathematically justifiable. So if we look at the RCV1 corpus, and let's say we plot log of t here and log of m here. Okay, so we are doing this kind of a plot, except that instead of plotting m versus t, we are plotting log of m versus log of t. Then what Heaps law predicts is this dotted line, right? It predicts a linear relationship between log of m and log of t, whereas what is actually seen is this dark line. So for small values, for corpus sizes that are small, t is going to be small, so log of t is going to be small. For small corpora, you can see that the actual values of the vocabulary size don't exactly match with the prediction of Heaps law. But as you move to larger and larger corpus size, you can see that both of them approximately, they fit pretty well actually. Right? So how many of you have done least square fitting in any of your courses? Are you familiar with the idea of linear regression? Right? If you have a bunch of data points like this, and if you want to, so this is the variable x, this is the variable y, and you want to express the relationship between y and x in the form of a straight line, least square fit allows you to come up with the best possible straight line to express the relationship between y and x, right? And the best possible straight line is that which will go through all these points in such a way that the error is minimized. Okay, the error as given by the difference between the value, the actual value and the value predicted by this line. So these error values are minimized. So the sum of the squares of the errors, if you minimize the sum of the squares of the errors, you get you get the value of this parameter y is equal to mx plus c. If you assume a generic straight line y is equal to mx plus c, you can estimate the value of these parameters m and c, which minimize this least square error. Okay, so that I mean, if you've done a basic course on statistics, you would have done linear regression. Are you familiar with linear regression? So I couldn't hear you.
Yes, sir.
Oh, you're familiar. Okay, good. So if you you can turn off the microphone. So if you compute the value of m and c, if you compute the equation of this straight line minimizing the least square error, what you get is that log of m is 0.49 times log of t plus 1.64. So this is the best fit line, this dotted line. And these are the values of the parameters you get. So this is the relationship between log m and log t, and you can express this as a relationship between m and t, right? Just by taking uh, uh, 10 to the power of both sides, you'll get m is 10 to the power 1.64 times t to the power 0.49. Okay, so you can see that the power here is approximately 0.5 and the value of k here is approximately 44. So the prediction of Heaps law, when you have a corpus with say a million tokens, is 38,323 as per this dotted line, and the actual value you get is about 38,365, which is pretty good, right? So if you are starting with a corpus, let's say you want to build a search system, you're starting with a particular corpus, you can count the number of words in your corpus, right? Count the number of words or tokens in your corpus, substitute it into Heaps law, and you'll be able to estimate how large your dictionary will be when you actually build the index. So you can plan for choosing a system so that your system can handle a dictionary of that size. So you may try this as an exercise later on. I would have actually done this exercise, but I won't since we're running out of time. Uh, what is the effect of including spelling errors in your dictionary? And if you're including spelling errors, then what you're doing is um, you're not doing document correction, that is, right? If you do document correction, then spelling errors won't enter into your dictionary. But if you allow for spelling errors, then you'll be increasing the size of your dictionary, right? You'll be increasing the number of tokens, and so you'll be increasing, in a non-positional index, you will end up increasing the size in the number of terms in your non-positional index, because the number of tokens will always be equal to the number of postings in a positional index. But in a non-positional index, by including spelling errors, you're adding extra postings list for those error terms also, for those incorrect spellings also. So your index size is going to go up. Whereas if you automatically correct for spelling errors in your documents, then your dictionary size is going to be small and you won't have postings lists for those erroneous spellings. Now this is something you may want to do. This is actually a very simple calculation if you end up, because the numbers have been chosen such that they end up cancelling each other neatly. So compute the vocabulary size M for this scenario, right? And the scenario is that you're looking at a corpus of web pages, and what you find is that when you look at the first 10,000 tokens, right? Let's say I choose the first 100 documents from the corpus, which gives me about 10,000 tokens. For 10,000 tokens, I find that there are 3,000 different terms, right? So these 10,000 tokens end up having 3,000 different terms. Then when I look at the first 1 million tokens, I find that there are about 30,000 different terms. Now my actual corpus may have a total of 20 billion pages, each having 200 tokens on an average. Now how do I estimate the size of my vocabulary if I look at the entire corpus? So what you need to do in order to do this exercise is you have to take these values which are given to you and you have to compute the values of the parameters here, m and c, right? Assuming a linear relationship between log m and log t, you can plug in t is equal to 10,000. For at t is equal to 10,000, m is equal to 3,000. At t is equal to 1 million, m is equal to 30,000. So using those two equations, you can solve for the two unknowns. And the two unknowns are the values of these parameters. Okay, the values of k and b. That is something you can compute. And once you've computed that, you've got this equation. You know what this dotted line is. And now when you're asked to compute the value of m, where the value of t is given as 20 billion times 200, then you can use that same equation to compute the value of m. That's how you're going to do. That's how you're going to estimate the size of your vocabulary in the whole corpus. Any questions on that? I won't go through the calculations since we started late today, so we don't have that much time. But any questions about the method that you would use to do this? Okay. So this was about trying to estimate the size of your dictionary from the corpus. What about postings lists? Is there something about postings lists that can be known before actually building the index so that I can plan for what kind of postings lists I'm going to have? So while Heaps Law deals with the vocabulary size in a particular corpus, it gives you an estimate of the vocabulary size from a particular corpus. We can also study something about the postings, and that's done by a different law. It's called Zipf's law. It turns out that in natural languages like English, there are a few very frequent terms and there are a large number of very rare terms. And that is what Zipf's law tells us. What Zipf's law tells us, again, it's an empirically observed law. And what it tells us is that if we look at the ith most frequent term in the corpus, okay, so let's say that T1 is the most frequent term. T1 is the most frequent term in the corpus. Let's say that T2 is the second most frequent term in the corpus. T3 is the third most frequent term in the corpus, right? So these are going to be basically stop words, right? Because stop words are the words which have the highest frequency. Okay, so if we rank the terms in the corpus in descending order of their collection frequencies, okay, collection frequency, recall, is the number of times a particular term appears in the corpus as a whole. And what we find is that the collection frequency of the term Ti, okay, so the collection frequency of the term Ti is proportional to 1 by I. What this means is that if we look at the most frequent term, let's say it appears CF1 times, right? So let's say that the frequency of the most frequent term is CF1. This is the number of times the most frequent term appears in the corpus. Then what Zipf's law tells us is that the collection frequency of the second most frequent term will be half of that. The collection frequency of the third most frequent term will be 1/3 of that. The collection frequency of the fourth most frequent term will be 1/4 of that. So if we were to plot the collection frequency of the ith most frequent term, okay, if you were to plot kind of a histogram where the height of the the histogram gives you the collection frequency, then we would get a histogram like this. We would get something that decreases like this. So these are the most frequent terms. Okay, and this is the number of times those most frequent terms appear in the corpus, the height here. So there are a few terms here that appear a large number of times. Okay, those are the terms in this region. And then there is something called a long tail. Okay, so the vast majority of terms appear very few times in the corpus. So this tail is very long. It is going to continue on and on and on. That's the shape of this histogram. So notice that this height here for every term is pretty much going to be the length of the postings list for that term, right? At least in a positional index. Right? In a positional index, the number of postings for a particular term is going to be the number of times the term appears in the corpus, right? So this means that our postings lists are going to be distributed in this way in the index. There'll be a few postings lists that are very long, and then there'll be a large number of postings lists that will be very short. In fact, what we saw from the table that I showed you earlier is that if you remove the top 30 stop words or top 150 stop words, that is, if you just delete these terms from here, recall how much the size of your index goes down by, right? How much the size of your postings list goes down by. It almost becomes half of what it was before the elimination, right? So it decreases by almost 47% here if you remove the top 150 stop words, and that's because most of the the stop words, the top 150 words that you'll be removing, are going to have very high collection frequencies compared to the ones that are coming below. Okay, so the collection frequency of the ith most frequent term can be expressed as is inversely proportional to I. So this can be written as the collection frequency of the ith term is equal to some constant k times 1 by I. And obviously this k is CF1, because if you put I equal to 1, CF1 is just k. Okay, so that's what Zipf's law says. Zipf's law predicts that your postings list will be distributed in this way. There'll be a few postings lists that will be very large in length, and then there'll be a large number of postings lists that will be very small in length. Okay, so if the most frequent term, and in the English language the most frequent term is the article the, if that occurs CF1 times, if this is the collection frequency of the word the, then the second most frequent term in the language, which is of, is going to appear approximately CF1 by 2 times. The third most frequent term, which is and, will occur CF1 by 3 times. Anyway, and in general, the ith most frequent term will occur k by I times. So again, we can take the log of both sides here, and we can express the relationship between log of the collection frequency of the ith most frequent term and log of I as this kind of a straight line, where the slope of the straight line is -1. Okay, so again, it's a linear relationship where the slope is -1. And again, this is a power law relationship, because after all, this can be written as CFI is k times I to the power -1. So this is also a power law kind of relationship, as we saw in Heaps law. Although of course the parameters and the nature of the equation is different, the values of the parameters. So let's look at how um, Zipf's law fares on the RCV1 corpus. So this straight line that you see over here, so what have we plotted here? This is log of I, and this is log of CF of I. Okay, so we are plotting log of CF of I and log of I. Log of I on the x-axis, log of CF of I on the y-axis. And what we see is that this straight line with a negative slope of -1 is what is predicted by Zipf's law. But what we actually find in the RCV1 corpus is that the relationship looks like this. Okay, so this does not exactly fit with Zipf's law, but it's, you know, it's a reasonable enough approximation that we can that we can say that this definitely holds. Okay, so even though the fit was not so exact, it turns out that this kind of a pattern in general is seen to occur, which is predicted by Zipf's law, and it's also seen in practice. Even if, you know, there's not a completely neat match between the values predicted by Zipf's law and the values actually seen.